Okay, we're going to look at a mathematical example of superposition of net force on an electric charge, so electric force with charges along a line. And so our question reads that using this figure, we want to determine the electrical force on charge Q. So this one right here, that sort of orangey color. Positions are given, and the charge of that Q represents is 2.0 microcoulombs. So what is the net force on this charge Q? All right, so in order to find the net force on that charge, we need to look at all of the interactions of each charge on each other. So this net force Q on this charge, the force this experiences from the pink charge, and the force Q experiences from the green charge. So to identify things a little bit easier, I'm going to call this charge A, this one charge B, and this one charge C. So we want to look at the force Q experiences from A, Q experiences from B, and Q experiences from C, and then add them all up vectorially. So we always want to remember to add them vectorially. So let's look at them individually first. We want to remember that we're going to be using Coulombs' law to find the electric force. And the electric force calculation for Coulombs' law, the magnitude is K, Q1, Q2 over the radius squared, where K, remember, is equal to 8.99 times 10 to the 9th newtons meters squared per coulomb squared. All right. And we want to keep in mind that the direction, if I get a positive force value, that means it's repelling. And if I get a negative force value, that means that it's attracting. And then I need to consider the actual direction of that force in order to determine if it's to the right or to the left. All right. So let's start with the force that QA, the charge represented, the electric force on my value Q by charge A. Okay, so I'm going to use my Coulomb relationship, the 8.9, reverse that, 9.88. That's what I was going to say, but it's 8.99 times 10 to the 9th. Q1 is negative 2 times 10 to the negative 6th coulombs. Q2 is positive 2 times 10 to the negative 6 coulombs, all divided by my radius of 3 centimeters, so 0.03 squared. So K, both charges, this Q and this Q, divided by 0.03 squared. And when I get that, I get a value of negative 39.96 newtons. What does the negative mean? Negative, remember, meant it was attractive. So these two attract. So what does that mean for my Q that I'm interested in? Well, an attractive force between these two tells me that Q I'm interested in is to the left. So this force on Q by particle A is going to be to the left, right? So again, the difference between thinking about what the negative represents for my electric force, and then what does that tell me about the direction? So when I want to look at the net force, I'm going to consider that in our Cartesian directions. Okay, that was the first force. Let's look at the force that object B exerts. So the force on Q from our object B. Right? So we have 8.99 times 10 to the 9th. Object B is negative 2 times Q. So negative 4 times 10 to the minus 6th. Then we have our object Q, which is positive 2 times 10 to the minus 6th, all over their radius 0.03 centimeters, or sorry, 0.03 meters, 3 centimeters squared. All right, so what do I get in that? We get 79.91 newtons. Negative. What does the negative tell me? It tells me the electric force is attractive. So I need to go look at my picture. Here's Q that I'm interested in. What does attractive mean? It means it's headed in that direction. So in this case, that attractive force is to the right. All right, so let's look at our last one. Object C. Oh, I think I'm gonna run out of room down there. We'll do it up here. So the force, electric force on Q by object C is equal to 8.99 times 10 to the 9th. Object C is 3Q, so 3 times, and it's positive, a positive 6 times 10 to the minus 6th. Q, of course, is a positive 2 times 10 to the minus 6, all over the radius of 9 centimeters, so 0.09 squared. All right, when I plug that all into my calculator, we get a value of positive 13.3 newtons. Now, what does a positive electric force mean? It means they repel. And so what does repel mean in my situation? Well, if Q is going to be repelled by object C, that's to the left. So that is to the left. So now we can look at the net force acting on Q. If I were to draw a free body diagram of Q, I have one force of 40 newtons to the left. I have one force of 80 newtons to the right. And I have another force of 13 newtons to the left. Okay, so I have my three forces. They're all along that horizontal plane. We have our net force then equal to negative 40 minus 13 plus 80. Our net force on Q is a positive 27 newtons, which is to the right. All right, so taking apart each one of the situations, looking at interactions two at a time, and then recognizing that these are all forces acting on that object, we can add them vectorially to get our net force acting on the object. The other point to keep in mind is that the electric force by Coulomb's law, what do our positives and negatives represent? And how does that translate to the actual direction of the forces acting on the object? All right, good job.